One of the main messages that we want to put out today and have you thinking about as you go forward is that science through computing is at best as credible as the software behind it, right? And if you think about it, this makes a lot of sense. We can talk a little bit about why as we go through this discussion. There are a lot of challenges that we face with our software and with our research. And this typically involves, we're interested in, we're interested in getting a better understanding of science, so we want to improve on the physical models that we have, and we implement a higher fidelity model, and that requires more and different solvers with more sophisticated capabilities, and those require more hardware resources. And we get ourselves into this loop where we're doing more complicated hardware and larger simulations and things like that, and that gives us a better understanding. It drives even higher fidelity models, and this is a feedback loop. And where we are at this point in many communities is that the science that we're pursuing has grown so complicated that these models have many moving parts, and there are many people needed to create and maintain many of these models and to use them effectively as well. So there's some really important considerations here in how to work in this type of environment. And so we're talking about ideas like separation of concerns so that people with different domain expertise can contribute effectively together to a project. And really, finding ways for people with different roles to work together on the same large, complex piece of software really requires sort of defining the rules for how you interact and how you're going to do things. And then you complicate this basic consideration of we've got this big, crazy software package that we're all contributing to, and then you have to also accommodate these high-end platforms that keep changing, and they're now more heterogeneous, and they have different types of now GPUs, and people are talking about AI accelerators and FPGAs and things like that are coming back. And so we don't know, oftentimes these codes live for years and decades. We don't know initially what all the requirements are. So we have to plan to be flexible and to try to be able to accommodate the change. We don't know exactly what changes will occur, but we know changes will occur. So we need to have ways of accommodating that in our software processes. And so these are some of the drivers that move us in these directions. And there are both technical and sociological challenges here. In the technical sense, all parts of the model that you're working on can be under the subject of research. And the requirements, as we mentioned, change as throughout the life cycle as you better understand the problem and as your understanding of the science grows and things like that. And we mostly do numerical simulations, floating point simulations, which have their own particular complexities with the numerical representations, and then how do you verify those things, and what is a tolerable difference. You can't expect bitwise reproducibility on most platforms these days, so how do you ensure that your software is doing what you think it should be doing? And then, we're trying to model the real world in many cases, and the real world is messy, and as we refine our models, they become more sophisticated, they become messier, and the software that represents that also ends up becoming messier and more complex. And then we have huge increases in the architectural diversity of the systems that we're working with, especially in the last 10, 15 years. Excuse me. Then on the sociological side, we have, in most cases, we have competing priorities and incentives. So, we have a limited amount of funding from our sponsors, and they may care more about publications than about the software per se. They want science. That's what they're funding. But then the software is the tool that gets the science done. So how much weight do you put on the software? And balancing the need to develop the software and add new features and things like that with the need to maintain what already works, to port all old working stuff and the new stuff to the next platform, and then using it as a tool for your research. We all have limited resources to do this, so we have to balance these things out. And then, as I mentioned before, we have an increasing amount of interdisciplinarity in the teams that are developing the software. So we need many kinds of expertise to be successful in the long run, but that also complicates the process of working together and communicating together. There are a lot of possibilities for failure, and just want to talk through a few things. Some really visible ones. You may have heard of back in the 80s, there was a machine, radiation therapy machine called the Therac 25, and a lot of poor design and development and testing decisions allowed flaws to creep in that led to at least 6 known deaths due to radiation overdose, or I'm sorry, three deaths, but at least 6 overdoses. And then in 1999, the Mars Climate Orbiter was lost as it was trying to insert into Martian orbit. And it turned out, you may have heard or you may remember, that it was a discrepancy in the units that were used, units of measure used by 2 different software components. So one component didn't follow the specifications. There was obviously inadequate testing at the interface to detect that. And it turns out, when they dug deeper, that concerns were raised earlier in the mission, but they were ignored because they weren't raised on the proper form in triplicate, whatever was required, right? This is NASA, after all. So, these are just a couple of examples. Some more recent things. So in the early days of COVID, Neil Ferguson at Imperial College is a epidemiological modeler, and he jumped in on COVID and did some modeling and then testified before the UK Parliament, and that influenced some of their early decisions about how to handle the pandemic. And so that was April 2020, and then March 2020, and then in April 2020, an independent climate science researcher, that's what he calls himself anyway, he says, I can't easily see where some of these assumptions come from. So the code was available. He can't see where these assumptions come from. The computer code is old, unverified, documented inadequately, if at all. And so this started a whole flurry of things. The press picked up this story because, of course, COVID is became a very controversial thing. And so you had a lot of people saying, we'd fire anyone for developing code like this. Models must be capable of passing basic. So this was a random stochastic model. So reproducibility in such a situation is a bit of a trick. How do you handle that? So a simplistic thing is producing the same results given the same initial set of parameters. Well, that's not usually a characteristic of stochastic models. So impossible to reproduce, first of many bugs, things like totally unreliable, buggy mess. So got a lot of press, most of it not very good. And this was just somebody's research code that they used for years and years, and they applied it to COVID, and suddenly it got a lot of scrutiny. What you may not have heard in the aftermath is that the folks at Imperial worked with Microsoft to refactor the code and clean it up so you can get a newer, better version that's out on GitHub. And then someone else took a look back at all these criticisms that had been leveled at the Imperial code, and he said, many scientists write code that's crappy stylistically, but which is nevertheless scientifically correct. And he said, professional commercial software developers are well qualified to review code style, but most don't have a clue about checking the scientific validity and what counts as good scientific practice. And so within our group, the Ideas Project, that led to some further discussions, which we'll get into in a second. But the other sort of the capstone of this story is that an organization called CodeCheck, which in the UK independently reproduces results. You can sort of go in and ask it to reproduce results if you want. And so they did a reproduction study of these results that Ferguson's team had, and they were able to verify actually that was reproducible. So some observations. First of all, your code's likely to live longer than you expect. And it's also very possible that it'll be used in ways that you have no idea, okay? So these are things you have to plan for. And this is especially the case if you're in realms that have any connection, any possible connection to policy, right? Climate modeling, epidemiology, there's a lot of other things that these days could touch on that. So increasingly consequential decisions are made on the basis of computational results. And so I think there's a reasonable expectation that the codes generating those results should be subject to greater scrutiny, okay? And the credibility of the science is strongly connected with the credibility of the software, which in turn is related to good software engineering practices. In this story, the COVID story, we heard about documentation, we heard about testing and verification and validation, and we heard about things like code readability and quality metrics, right? These are very straightforward, simple things at some level. You say, yes, they should be better, but they can also, they can become things that people will rally around to say, oh, that's bad, and we shouldn't be making policy based on this, or things like that. And then in our group, we talked about this thing that Phil Butt said, should we excuse scientific software for being crappy stylistically? And the conclusion we came to is that we know that happens, but crappy code makes it easier to hide bugs. If you have nice, clean code, it's harder for the bugs to hide. And so yes, at some level, but it would be better if we did a better job with our software. And there can be more subtle impacts too. Anshu's team at the Flash Center back in 2005 had a chance to, were you there? Okay, he was with the Flash Center later. Had a chance to access, at that time, the largest machine in the world, which is a Blue Gene L, for a dedicated run. They didn't have a lot of time to prepare for this run. They were given about a month to get ready for a 1.5-week run. And although they had good software development practices in place, to do this run, they needed a particle tracking capability in the code that wasn't ready. So they had to do some quick and dirty work to get that going. And it turns out that in that work, they had an error in the particle tracking. And they got the runs through, but they then had to spend 6 months dealing with this error that had been introduced to get actual results out. So they had good software practices in place. They test regularly. You'll hear about some of this stuff from Anshu because her talks are based largely on her experience with the Flash codes. But there was a reason they couldn't do their usual level of rigor here. They just didn't have time. And because this was a priority opportunity. And so they ended up with technical debt that they had to deal with. So you may have heard, how many of you have heard the term technical debt? Okay, a good third or so. So technical debt is basically the implied cost of having to do more work because you've kind of done a quick and dirty job initially, some kind of limited solution to the problem. It's like monetary debt. The more technical debt you accumulate, the harder it is to pay off. So it increases the cost of maintenance. Parts of the software may sort of degenerate and become unusable over time. And if some of the debt is associated with the verification process, then you may have inadequately verified software, which may not give you correct results. It tends to increase the ramp-up time for new developers, and overall, it reduces both your software productivity, your ability to move the software forward, and your scientific productivity. And if you're working on high-end supercomputers, these are valuable resources that, like a physical facility which has a very expensive beamline that's 20 miles long and huge detectors and things like that. These machines cost hundreds of millions of dollars. They cost millions of dollars to operate each year. And people obviously pay for that, even if you don't have to pay for the allocation, right? And so effectively, when you get time on these machines, you're getting effectively a bunch of money. So the sponsors concerned in giving people access to these resources, are you being a good steward of the resources? And your concern should probably be, are you getting the most possible out of this allocation that you have? Are you getting the most scientific productivity, right? And I think these are valid questions to ask, but it's also, you can look at it flip it a little bit and say, are you going to make the best possible use to move your own science and your own career forward out of this allocation, right? So these are things to think about. Fundamentally, we end up with this loop. You end up at the same place both ways, I think. Good scientific process requires good software. Good software practices increase software sustainability, and software sustainability increases scientific productivity. And good software practices also directly increase scientific productivity. So you can see it from all different directions, really. And that's kind of the message that we would like you to be thinking about throughout this and as you go forward. It really needs to be something that sort of becomes ingrained in your thinking. And if you can do that, it doesn't necessarily have to be hard to do. So let's spend a few minutes actually talking about good software practices. There's no fixed, universally agreed set of software best practices. It depends to a significant extent on what your software and your team need to do a good job. But there are some things that are generally understood to be beneficial and to many people think of as a baseline. And so let's talk about some different perspectives that people have published on these. So this is, first one is a paper called Best Practices for Scientific Computing. It's by Greg Wilson and a team of others, and the DOI is up there. So their messages are, first of all, write programs for people, not computers. So try to make your code readable, make your names meaningful, use good code style, and keep the formatting consistent. Let the computer do the work wherever possible. So make the computer do repetitive tasks. So script those things and what have you, and build up automated workflows if you're doing things in a repetitive way. Make changes incrementally. Don't just do whole hog some huge thing and expect that it's going to work. Just make it as incremental as you can. Save your steps using a version control system so that you can track and backtrack if you need to. Don't repeat yourself. Plan for mistakes. So add checks to your programs. If assertions that where you know certain things should be true, and especially if you can test them with minimal cost, so you're not making your program run longer, but conservation rules and things like that. Use unit testing, and when you get bugs, you can turn them into test cases so they don't reoccur in your software. Learn how to use a debugger. Optimize your software only after it works correctly. So first, get it working, then worry about how it performs. So document the design and the purpose of the code, not the mechanics. You don't need to have a line that says A plus 2 and have a comment that says increment by 2. You might want to say why you're incrementing by 2 and what you're incrementing by 2 and things like that, right? We won't talk in this today about code refactoring, but this is a way of evolving code to improve it. If you're finding that you have to write a lot of documentation to explain how things work, you may be better off rewriting the code in a way that sort of simplifies it. That's basically what that line means. let's see, and then we'll mention code reviews as a very useful technique. Pair programming is sort of live code review in a sense. Use issue tracking tools, some very things that are, I think, a lot more known today than 10 or 15 years ago and recognized, maybe used, maybe not, but they're really valuable practices as a baseline. These folks, a few years later, realized that the best practices were really maybe too high a bar to set for a lot of teams. And so they came out with another paper of good enough practices, right? And so they focused on data management. They had ideas about how to work together on manuscripts, how to some aspects about the software. These sort of cover a bunch of cases: decompose into programs into functions, be ruthless about eliminating duplication, make meaningful variable names, make dependencies and requirements explicit. There's a whole bunch of details in here, and I'm not going to go over all of them, but you can see they've given this. So this is more extensive, but it's also sort of a little bit of a lower, more general level. Ideas for collaboration, how to organize projects, which they hadn't talked about before, keeping track of changes as version control, and some approaches to help do that. And then one other set of best practices that I want to talk about, which is a little bit different. So those others two came from folks who do scientific computing and work in these spaces. This comes from the Linux Foundation, which is, the folks behind the Linux kernel and a bunch of other, system software types of things. And so they have a very extensive set of best practices, and they have 3 different levels. You can be passing, silver, or gold. And these are, it's very, getting gold is very stringent set of requirements. But they define a set of must-have and should-have criteria, and I just want to look at the headlines on these things. Each of these is accompanied by an extensive set of points that you should satisfy, and they have references and justification for all these. This is a really useful, even if you're not going to do all of this, looking at this Linux Foundation idea of best practices gives you a lot of pointers to justify making the case for why you should be worried about these things, why you should be paying attention. So these folks are all about open source, so they want you to have an open source license. You need to have certain kinds of documentation. You need to have defined project oversight, version control. You need version numbering on your software. You have to have a bug reporting process. There's a bunch of things about quality and how do you ensure quality in code. They're also concerned about security, which is not something that a lot of scientific software developers have historically been concerned about, but becomes more of a concern as we do more interconnected computing workflows that work across systems, and they get into managing instruments and things like that. And so these become more of a concern, and there's more awareness in our own community, scientific community, about this now. Using analysis tools, you should be using static analysis and dynamic analysis tools. Excuse me, things like that. And if you may not be aware of all these terms, but we can talk about some of these things if you want. But I encourage you to go take a look, even if this is completely aspirational for your team. But it may give you some ideas as to things to think about and why with the justifications, and some of the specific criteria that they set you may find useful. So basically, these are certain people's ideas of what constitute best practices for software development. But I think one of the really important messages that we also want to send today is that whatever you see, whether it's here in these discussions or out on the internet or in a book or something like that, you should think about that maybe it doesn't apply directly. Sometimes you'll look at this and you'll say, well, there's no way I could do that with my team. But maybe the way you should approach it is there a kernel in there that would be useful to my team? Would it benefit my project? And how can I adapt it to work for my project? So you should be thinking about these things that you hear in terms of how does this work, how might this work for us? For scientific software, which has a kind of a different way of working than a lot of other software development, and for your particular team. And so you may find things that you'll need to adapt. You may find things that you can just adopt whole hog. And probably you'll find, different ways of approaching things. Then you may need to talk with your team to see what would go over best. What the only software practices that are useful are the ones a team will adopt and use, right? So don't be afraid to experiment. And as you're trying this, to try out things and see if they work and see if they stick. So then people ask, well, I'm a scientist. I'm supposed to be doing my science. How much time should I spend on my software engineering? And I think our answer for that is your project should include just enough software engineering that you can address both your short-term and your long-term scientific goals effectively. So keep the focus on the science, but ensure that essentially your software is a tool that's well honed to give you that edge in getting your science done. And how can you keep it that way? So one of the approaches that we've developed and that we advocate is something called productivity and sustainability planning. And it's a fairly straightforward process that says we're going to identify the pain points that our team has in software development. And we're going to pick one thing as a goal that we're going to work on in this cycle. This is an iterative process. And we're going to try to target processes and behaviors, not just tasks. Not, we need better documentation, but how do we ensure that every time we have a new commit, that it has the appropriate documentation associated with it? And that doesn't get deferred for 3 months, which ends up getting deferred until never, and things like that. And so pick something you can address in a finite amount of time, maybe a few months, agree on a plan to address it, and then develop a set of markers. How will you track your progress towards getting to a point where you've achieved the goal? And that's your progress tracking card, and then you can work the plan and you can track your progress. And when you're done, you can celebrate and then move on to the next pain point. And so the overall goal with a process like this is to sort of bend the curve. So if your original processes would lead you in this direction, the new process might take a little bit more work initially, but the intent is that it eventually flattens the curve. So it costs less overall to get where the level of progress that you want. And we've got, in this page, we've got some links to tools that might help you with understanding where your software and your project might be able to use some help. Progress tracking cards, we have a lot of examples. The whole PSIP process is documented. And then the bssw.io site, Better Scientific Software site, has resources that might help with some of these things. And if you have your own experiences like this, please consider contributing. So we'd love to hear about that. So in today's tutorial, there's a lot of topics. Well, in general, there's a lot of topics that could help you improve your scientific software development processes. We're going to focus on a few because we have only a limited time, where the software engineering advice out in the wild typically doesn't address the needs of scientific software as opposed to more general software. So we're going to be talking about designing software for flexibility and extensibility in the context of science, testing strategies for these really large complex software systems that we often deal with, building and packaging, and then how do you take these things into production and use lab notebooks and manage these computational experiments that you're doing, and then also how can you understand your own software development processes and tools that can help you do some of that. So, and one of the reasons that we're focusing on these topics is because these are the things that we think become particularly challenging when you're working on extreme scale systems, trying to do extreme scale science. And so with that, I think we're at the end of the first section, so, or the first talk. Anshu can come up, and I'm happy to take a few questions if you have any right now.
I was wondering, what did you mean by crappy stylistically?
Okay. It's one of those things where I would say when you see it, you'll know it. So I don't know. So when I write software, it always is nicely formatted and has nice comments and describes things, what I'm doing, and what have you. But when my colleagues write software, they're not concerned about that. They're just hacking out code, right? And they're not, they have A and A2 and A3 as variables, and they're doing all, the function names or method names don't make sense, and they have, spaghetti code that just jumps around, and right, that's kind of the kind of thing I mean. So if you know what a code formatter or a linter is, if you ran a formatter over it, it would improve things and make it more readable and less stylistically crappy. There are other ways you can improve it too.
You had mentioned developing recommendations that users then actually adaptability of those recommendations. What recommendation currently, I guess, and how do you navigate the process of figuring out what people would actually adopt versus what sound recommendation that they really should work hard to try to actually incorporate?
A lot of it just has to do with talking with your team. Of course, it'll depend to some extent on how the team is structured and organized. It may be a bit top down. For example, your professor might say, this is the way we're going to do it. But if you have a little bit more democratic team, then you may need to discuss, is this reasonable? Will you guys do this? Things like that. And so there's a very big social component to this, and it involves communication. And you really just have to, somebody will say, that's complete crap, I'm never going to do that, or then you need to find a different approach maybe. Or maybe be able to convince them that they should actually do it.
I was going to revisit the crappy stylistically question.
Okay.
I think one thing to remember there is it's not just about writing comments and using good variable names and doing things right, when you write code all at once. So we had a team at Livermore where they sort of accreted changes over time that eventually made for a sort of bad situation. So they had a dependency library that knew a whole lot about its dependence and the way that they were using it, which made it really hard to reuse in another application. And that's not the kind of change that anybody sits down and does once. Although I would argue that scientists are more prone to do that sort of thing once than other people, because scientists are awfully clever and they have a really high tolerance for complexity, which is not always the greatest thing when you're engineering software. So watch out for those kinds of things that need refactoring over time too.
All right, take one more.
So it's just following up on convincing people to adopt these practices. Do you have any recommendations for metrics for showing how the software has improved productivity and science?
Yeah, so metrics are always a challenge, and Boyana is going to talk about that. She might want to address that now in a second. But oftentimes, it's good to find evidence to help support your case, why you want to do something. And there are, for many things, there's stuff out in the software engineering literature that you might be able to find. And then Boyana, you want to give a little preview of where you're headed?
I'm going to show some metrics. They may not be what you want, but they'll give you ideas of what is possible to measure.
But and she's developing tools that will do that mining and help you compute those metrics. But that's for your software. Some of the evidence that might help convince your colleagues to adopt a practice is would be out there from other projects, right? So you would want to find something that's already been done that says this is effective.
The other thing with metrics that's kind of tricky is I think a lot of productivity metrics ultimately, or a lot of the ways that productivity increases is more of a weak scaling thing than a strong scaling thing. So like a lot of people are looking for productivity metrics that are like, this made me write my code this much faster. When actually the productivity tool let you do more with more software as opposed to what you were able to do in the past. It didn't necessarily speed anything up, but it made your end result bigger. And I think people have a harder time understanding those metrics.
Thanks. So if you have more questions, you can put them in the Slack.